So in number 3, a point moves along a curve y equals x minus 3 squared, such that its x-coordinate is increasing at 4 units per second. At the moment x is equal to 1, how fast is the y-coordinate changing? All right, so it's basically giving us a nice little recipe here. They're telling us that the x-coordinate is changing or increasing at 4 units per second. So that's the dx dt. And it's increasing, so just keep that in mind. Because if it's decreasing, then we slap a negative onto that, whatever that number is. All right. They're telling us that x is equal to 1. So we can jump right into the derivative part of this. All right, so y is equal to x minus 3 squared dy dt. So it's definitely chain rule in its current form, but it's like baby chain rule, right? Because the inner function has a derivative equal to 1. So if over the break you forgot everything about chain rule, you'd probably get away with it on this one because the inner function is just a 1. But then because it's a related rate situation, I have to take the derivative with respect to t. So the derivative of this is 1, but multiplied by dx dt. And it's easy enough to distribute out also, and then just go with the power rule. If you did that, you get 2x minus 6 when you take the derivative. Well, 2x minus 6 times dx dt. All right, so we could plug and chug now. We're looking for dy dt. So it's going to be 2 times 1 minus 3 times 4. So is that negative 16? And so the units for x, there's no reason to think the units for y would be any different, were units per second. Shouldn't even be awake right now. Got another hour and a half before I should be waking up. At the moment x equals 1, how fast is the point's distance from the origin changing? That's a little bit more interesting. This is obviously a parabola, but part B is not really asking about movement along the parabola directly. I mean, indirectly, definitely. Let me just do a quick sketcheroo here. My y-intercept would be 9, right? That's like something like this. At the moment x equals 1, and 1 corresponds to 4, right? It's talking about the distance from the origin. All right, so you could use distance formula. You could also use Pythagorean Theorem. All right, if we use Pythagorean Theorem, I think the work is a little bit easier. So make a triangle. I mean, any distance can be decomposed into horizontal and vertical vectors, so there's no reason not to. I mean, if you like the distance formula, that's fine. It's just, it's a radical containing 2 squared binomials. It's going to be chain rule within chain rule. So it's going to be doable. You'll get the right answer. I mean, you're not going to fit it in that space, but that's par for the course in this class, I guess. So yeah, it's just going to be a lot more work, I think. All right, very doable, but probably not what you want to do. All right, so we have an X, we have a Y, and we have a D. That's going to look weird. I'm going to call it R. Because when I take the derivative, I'm going to have like d something. It's just, I'm not even going to like saying it, so make it a dr. And generally, the hypotenuses are abbreviated using r's, just in general, whenever you're dealing with triangles, for some reason. The reason is that any line segment could be thought of as the radius of a corresponding circle, which is really kind of strange to think about. But in Calc 3, so that's 2 levels. Well, if you test out of this one, yeah, so it would be your second semester in college if you were to go a pure math route. You'll learn about how to parameterize. It's pretty cool. But really what happens is you'll have some kind of curve. And instead of thinking about it in terms of x and y values, you'll think about it in terms of radii. So every little distance along that curve, like this little guy here, you'll say, all right, that's a good little curve. I can find that little segment there, or I can think of that as a tiny little arc length of a corresponding circle that would have its own radii, and define the circle, and then work off of that circle calculus. The reason behind that is, whether you like it or not, trigonometric calculus is a whole lot easier than non-trigonometric. The idea behind that, and it doesn't seem like that's true. It's like he's lying. He's clearly lying to us. Like the algebraic stuff only goes so far. You know, there's only so many things you could define with simple polynomials, radicals, rational expressions, things like that. Eventually, the algebraic expressions get so cumbersome that you need to move away from them because they're not things that you can take the derivative or antiderivative of. Okay? So we end up needing trigonometry. But the fortunate thing about trig is if I were to ask you right now what the antiderivative is of cosine, you can tell me that. But if I asked you what the antiderivative is of 1 over 1 minus x squared, it's going to take you a few more minutes. Right? So, by the way, what is the antiderivative of cosine? Yeah, sine. Yeah, because if antiderivative is the opposite of derivative, you're just thinking about the thing that gave you a derivative of cosine, and that would be sine. Right? So, the trig stuff is really where we want to be. Anyway, that's the justification for calling it R. It seemed like I'm answering a question that you didn't ask. Probably didn't necessarily care about. Might fall in the category of fun fact of the day, but at some point down the line, it'll be important. So x squared plus y squared equals r squared. We could, if we wanted to, take the square root and then take the derivative, because in fact we are looking for dr dt. You know, saying how fast is the point's distance from the origin changing. So I am looking for dr dt. If I solve for r, I'll directly be able to get that. The only issue is I'm creating the thing that I was trying to avoid with the distance formula, the radical containing a mess. All right, so let's take the derivative of this as is with respect to time. So 2x times dx dt plus 2y times dy dt equals 2r times dr dt. All right, none of these quantities are constant because depending on where I place that point along the curve, I'll get a different triangle with different legs, different hypotenuse. Right? Every length is going to be completely different. Right? So everything is changing. You know, if you can actually visualize this, I'll show you on GeoGebra tomorrow. It's really kind of cool. But if you slide the point along the curve, the corresponding triangle is going to change accordingly. Right? So there's no reason to think that anything's going to zero out here. There are situations, like in the very next problem, where part of it will zero out because the ladder's length is not going to change. Right here, the hypotenuse will change. One good thing is that the 2's are going to cancel out across the board. Now, it's a little something. All right, we're still talking about the x value of 1, which corresponds to a y value of 4. We figured out what dy dt was at that particular moment. The preamble said that we were looking at a dx dt of 4, so we have pretty much everything we need, or almost everything. So we're looking at 1 times 4 plus 4 times negative 16, that's what we got from part A, equals the r, which is not yet known, times the r dt. All right, just kind of off on the side. We have a leg of 1, another leg of 4, and I'm looking for r. Pythagorean Theorem. It's the sum of the squares, right? So, square root of 17. All right, so I'm taking the 4, subtracting from it was 64, so negative 60. Am I right there? 4 minus 64, negative 60, over rad 17. So dr dt. And these are linear units. We're not talking about area, volume, or anything like that. So the linear units are the same linear units that were used for x and y. So units per second. All right. So again, this is what I was talking about before. You look at negative 60 over radical 17. You're like, I don't know what that means. Is that a lot? Is that a little? I don't even look at that. I just look at the negative sign. That's telling me that at this instant, the length of the hypotenuse is decreasing. So it's getting smaller. So if you actually take 2 fingers and trace it along the curve, you can feel that happening. Right? So as you slide along the curve, you can feel your fingers getting closer to one another until you get to a particular moment where those fingers start getting further and further apart. There is some moment over here where your dr dt would become 0 and then transition from 0 to positive. Right? So that's where it starts increasing. So down the line, we'll start learning about how we can figure out that kind of thing. But you know, there's definitely some meaningful applications to it. So what I'll ask you to do for homework would be just the next 2 problems. I mean, I suppose you could do the next 3, but I wanted to talk you through the last one because there's some funk involved in it. Number 4, ladder 10 feet long, rests against a vertical wall. If the bottom of the ladder slides away from, I should have kind of made that a little better. Slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? All right, so get a little diagram going here to get a sense of what's going on. Create a wall of sorts. In case you don't know, that's what that is. All right, I'm gonna make a ladder leaning against the wall, probably not in a physically safe sort of way, but that's how I draw it. And get some ground here. All right, so the ladder is 10 feet long. All right, it's creating a Pythagorean relationship. All right, so we're operating under the assumption that the ground is horizontal and the wall is vertical. You know, it's not always something that you could assume. I mean, generally you could assume the wall will be somewhat vertical, but the ground, I mean, depending on where you place the base of the ladder, I mean, you could have any number of possibilities. So we have that. It's sliding away from the base of the wall at a rate of 1 foot per second. So let me define some variables for these dimensions. So I'll have the distance the ladder is from the base of the wall. We'll call that x. X for distance. And the height the ladder reaches up the wall, we'll call that y. Y for height. X and y make sense because if you're plotting this on a coordinate plane, x would be horizontal, y would be vertical. Okay. The hypotenuse is not changing, so we don't actually need a variable for that. Right? So that's one thing, that's the exception that I was talking about yesterday, where you don't want to substitute numerical values in unless you know that it's definitely constant. Because if you make a substitution, a numerical substitution to a variable quantity, when you differentiate it, it's going to go to 0. If it goes to 0, it's implying that it's constant. How could it vary if it's constant? That wouldn't make any sense. All right? But if you know something is in fact constant, then it could go right into your formula, equation, whatever it is you're using to define your related rates model. Right? So this is the Pythagorean relationship. We could state then that x squared plus y squared is equal to 10 squared. They're not talking about angles here. We're not talking about areas. We're only talking about linear measures related to the sides of a right triangle. So a Pythagorean relationship makes sense. All right. They gave us some information about the horizontal rate of change. They're telling us that dx dt, the rate of change in the horizontal direction, dx dt is 1 foot per second. All right. Direction's important. In this case, if you didn't consider direction, you'd probably get away with it because they said 1 foot per second. They said it's going away from the wall. All right. Going away from the wall. In this case, if the top of the ladder is sliding down, the base of the ladder is sliding out to the right. That's a positive movement going to the right. Right. So we'd be all right based on this diagram. But if I drew my figure the other way, the ladder leaning against the wall, coming in from the left, when it slides down the wall, it would actually be going, or at least it would have a rate of change of -1 foot per second because the movement would be to the left. So it is dependent on your diagram, and so you have to be careful of those little things. That's, the difference between a 4 and a 5 on the AP for that kind of question. So differentiate 2x dx dt plus 2y dy dt equals 0, right? Derivative of constant. Could knock off those 2's, divides out evenly. I have a related rates equation. All right, it's an equation that relates rates. The rates are the derivatives. We have one for one variable, the x, and one for another. So there is a relationship there. They're telling me that the x value is going to be 6 when all is said and done. Yeah. That's what I want. So I can replace x with 6. Dx dt I can replace with 1. Y, well, I'll figure that out in a sec. Dy dt is what we're looking for, so we're almost there. So 6 times 1 plus something times dy dt equals 0. All right, so if we could just figure out what that y value is, then we'll be all set. All right, so we know x at that moment, right? The ladder's in motion. We're rolling camera. We film the whole thing happening, but then we go back and watch the film again. Stop the clock when the ladder is, or stop the film, just hit pause when the ladder is 6 feet away. we would want to be, well, we would have a sense of what the rate of change is that was given, but at that moment, we'd have a corresponding value for y, which would be what? 8. So we know x at that moment would be 6, y at that moment would be 8. All right, it's a Pythagorean triple, all right, or you could just do it. 6 squared plus 1 squared equals 10 squared, right? So the 8 goes in my open set of parentheses, and then we solve dy dt is what, negative 3/4? So linear movement, same units as the units for x, and also for the length of the ladder. There's no reason to change it unless there's some indication in the problem that tells you that you should. All right, in this case there wasn't. The sign should be negative because as the base of the ladder goes out, the top of the ladder is losing height, so its height is decreasing. It's going in the negative direction. All right. Just based on the parameters of the situation, there is a relationship between the rate of change in the horizontal direction and the rate of change in the vertical direction, but it's not in lockstep. It's not for 1 foot of movement here, 1 foot of movement there. And that's possibly based on the fact that, let me just double check. Yeah, it could have something to do with the idea that the legs of the right triangle weren't congruent to begin with, or weren't necessarily congruent. So when you place the ladder, there's only one instance where the 2 legs of the triangle would be congruent to one another. So any movement beyond that particular moment would have rates of change that were necessarily different because they're just covering different distances over the same amount of time. Right. So yeah, that's one application of a triangle situation. Very quick and easy to do, although I've been talking about it for like 10 minutes. But when you do a problem like this on a test, you're done with it in like 2 minutes. Right? Because it's very easy to set up, very easy to carry out. You'll find that the Pythagorean relationships are the most common relationships, and they come up all the time. And when they happen, that's a good thing. You look forward to those. It's the weird ones where you have to invent a formula. We'll get to them. You have to invent a formula in order to solve the problem. That's when it gets a little crazy. Number 5, altitude of a triangle is increasing at a rate of 1 centimeter per minute, while the area of the triangle is increasing at a rate of 2 square centimeters per minute. At what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100 centimeters? All right, so there's a lot of moving parts here. But they're talking about altitude, fancy name for height, area. I know a formula involving a triangle that relates area and height. Half the base times the height gives you the area of a triangle. All right, so, and they're telling us that the altitude is increasing. So my dH dt actually, I don't even have to write equals. I'll just indicate that that's my dH dt. All right, so the altitude is increasing. So the height is increasing. It's a rate of change. So we know it's a derivative. Again, it's always implied to be an instantaneous rate of change unless they use the word average in the problem. Right? So at no point do they say average. So these are all assumed to be derivative results. This will give you a tip as to what the relationship is. Because sometimes, like it's supposed to be a rate, but a rate of what to what? Well, a linear unit to time. Right? Well, what's the linear unit related to? The altitude or the height. Right? So it kind of like steers you in the right direction in terms of how to define the variables. Right? The area is increasing at a rate of 2 square centimeters per minute. All right, so we have a rate of change of area. All right. At what rate is the base of the triangle changing? All right, so the base of the triangle. I could define that easily because in my formula, my area of a triangle formula, B is what I'm using to represent base. So this must be dB dt because the rate of change would relate whatever the change is for that base to the change in time that's been consistent throughout all these problems. When the altitude is 10 and the area is 100. All right, so this is good news, believe it or not. You look at all this and you say, well, okay, I have a formula and I have all these d whatevers. It seems overwhelming, but this is actually the best case scenario for a problem like this. What it means is that each one of these variables that are in this original formula, they belong there. And that's kind of strange to think about. It's like, of course they belong there. It's an area of a triangle formula. Why wouldn't it be there? The issue would be if they didn't tell me anything about the base, or if they didn't ask me anything about the base, then I would have a problem because I would have a B in this formula that doesn't correspond to any known information or required information. So then what would I do? Have an answer in terms of B, possibly. That's the best case scenario. The other situation, or the other way to account for it, would be to find some kind of substitution that allows you to take the B out. Maybe there's some relationship between the base and the height. Some ratio, some proportion that you could use to swap out B for H. But fortunately, that's not going to happen here because when I take the derivative of this, we're going to have dAs, dBs, and dHs everywhere. So we're in good shape, right? The formula corresponds to what the problem is either asking us or giving us, right? I mean, that's pretty consistent for most word problems, but even more so, I'd say, for this stuff. All right. The one thing you might not look at too fondly is the idea that, okay, so everything varies here. So it's not like the base is remaining constant while only the height of the triangle is changing, or the height remains the same while the base changes. Everything's changing. So you got a triangle that's stretching and skewing and misshapen and reforming. So what does that mean algebraically? It means that I have to treat everything as a variable. Nothing can be treated as a constant. Like in the last problem, we were able to say, well, the hypotenuse, in the problem prior to that, the hypotenuse was part of the differentiation process. In the last problem that we did, since we knew it was constant, we knew the derivative would just go to 0. We could take advantage of that. Here, all of that means product rule. All right, so dA dt is equal to, this will be my first, times the derivative of the second, plus my second, times the derivative of the first, which would be 1/2 dB dt. All right, so then we start popping our information in. I mean, we'll run into a little bit of a hurdle in a second, but it's nothing insurmountable. So we know that the altitude is changing and specifically increasing, because if it was decreasing, it would have a negative sign. So the dH dt part of this is going to be a 1. dA dt is 2. They didn't tell us B, so we'll sit tight on that for a second. Sorry, I gotta try to figure this out because my screen doesn't have the same dimensions as yours, so I only can see like this portion at any one time. All right, so I need to get B. I'm looking for dB dt ultimately. The altitude is 10, so I can pop that in. That's the one thing I couldn't see. So then the question is, all right, well, how am I going to get this B? Well, they give us some information. They tell us that if we're looking for all of this stuff to happen at the moment the altitude is 10 and the area is 100. So just kind of off on the side, just go back to your original area formula. All right, they're telling us that the area at that moment would be 100. The base is what we're looking for, but the altitude or the height is 10. All right, because we do have a relationship between A, B, and H. They flat out told us H and A, so that allows us to figure out what B is. So half of 10 is 5. Divided into 100 is what, 20? So B is 20. So I could chuck that in, right? Oh, poor quality 20. There we go. Kinda, a little bit better. So then I could just solve this. All right, it's all numerical now. All right, so I'll have a 10 here. Right, subtract it off, I get a -8. So this is a 5. So -8 fifths. And just be careful about units. All right, we're back to linear units because it's just a measure of a side of a triangle. All right, it's not an area or a volume, so centimeters per minute. So, getting a little beefier. This is like the most popular question though, for some reason. Calculus textbooks seem to love the inverted circular cone. I have one. It doesn't really help me explain the concept, but I need to break it out once or twice a year to justify the purchase because I believe they said it cost $250. No.
What? I'm sorry, what?
Way.
Yeah, the teachers always bring this out for like $250.
Yeah, I'm like, I didn't buy it. I wouldn't pay $250 for this. Oh, now it's inverted.
Oh, it's just upside down.
Yeah, yeah. They play fast and loose with the word inverted, like in like the real world. So like a Top Gun, inverted. You know, it's like an upside down.
Like the water cups.
Yeah, that's all it is. So when they're talking about an inverted circular cone, they're talking about this. It's great. It's wonderful. Yeah, but I mean, aside from giving you a sense of what the shape of an inverted circular cone with base radius 2 meters and height 4 meters looks like, it's not really going to tell you much. Let's hope it's balanced.
And the find the rate at which and the height of the.
I don't understand, like the paper cups that, you know, the cone-shaped ones.
Why do those exist?
Yeah.
Like, they don't. Who made that? Those are annoying. They just like.
They hold like a fluid ounce and a half of water.
They do, but the only thing I can come up with is that, like, micromanagers in like office jobs were like, listen, we don't want these people sitting around just talking to each other, drinking water all day. Make it so that they can't put the cup down. Then they'll drink it, throw it away, and they'll have to get back to work.
Or buy more.
Or throw it away, get a new one, and then go through like 30 of them in one session. Yeah.
Really, like, cheap to make, obviously. They require less material.
Yeah, it's like a piece of paper, glue, call it a day.
You just make a tiny cone cup that like doesn't last that long.
Money.
Also, it might be like, I might can't be. I have no so much for this stuff for some reason. I might can't be using it for like sports, or you just use it and go. So you could use my.
Huh. Yeah, because like if you're running a race, yeah, you don't need to put it down anyway, and it's cheap, I guess. I don't know. I like my backstory. Mine makes it seem like there's a sinister plot at work, like doing stuff like that. I don't know. But yeah, a water tank in the shape of that. Now they're doubling down on this concept, and that's just aggravating. Radius of 2 meters and a height of 4 meters. So that's like, well, definitely taller than the ceiling here. So, and it's an inverted circular cone. So they're like, not only are we going to make you drink out of these paper cups, but the water tanks that supply the paper, we're going to make those giant, like funnel-shaped paper. We're making it out of paper too. That's the thing on top of it all.
The world.
Yeah.
Like what?
You're like, okay, so that's one of those like,
There's like a water tower.
you're like,
just like a code on it.
Like with the cup, it's just one piece of paper. It's not like it's one giant sheet of metal. Like, it's just
right. But
How
I
can we
can imagine like,
stupidest looking water tower possible.
I'm just kind of visualizing a moment where I'm like, I can't wait to go visit,
I thought you said Burnett.
name a place somewhere other than here. I get off the plane, getting like Lyft, because Lyft or Uber is everywhere now, even in like the sticks. So I get in the car and I look out and I see the inverted circular cone water tank on the horizon, and I'm like,
Turn back.
turn it around, we're out of here. This place is filled with imbeciles. There's absolutely no way that makes it. I don't know. But we start with geometric figures that are not cylinders and rectangles and things like that. Water is being pumped into the tank at a rate of 2 cubic meters per minute. Find the rate at which the water level is rising when the water is 3 meters deep. All right, so, well, we need something that relates, and that's how you know what formula you're using. We need to relate volume to radius and height. All right. So you're reading the problem, you're saying, you're just kind of taking note, you don't even have to write it. But you're thinking, all right, they're giving me a volume, or they're asking me for a volume, height, radius. What formula do I know that's going to get me all that stuff in one shot? Right, well, it's generally going to be a volume formula. So volume of a right circular cone would be what?
1/3.
One third
R.
pi r squared h. It's been on my list of things to do, not in terms of like proving it, but just no, not even that. Like just playing with shapes and figuring out how 3 cones make one cylinder. Because
If
Good question.
you put like,
I mean, you have to take them apart, right? You like cut them in half and things like that, but
I was gonna say you like invert 2 of them and put them like.
it's just the amount of
That
volume.
would work.
You make that triangle with the circular top.
well, if you could do that, like you put 2 tip to tip and then use the other as the filling to build it up along the walls,
Yeah.
but that seems.
We do
Oh,
that with
oh,
clay.
you know what? I just totally figured it out. Oh wow, it's so
Now
crazy.
you have to draw it.
It's like an
There's
hourglass.
absolutely no way that's going to happen because I don't even have the drawing ability to. I mean, you saw my ladder a second ago. Like to draw this is going to be insane. All right, so the 2 cones tip to tip, right? And then the third cone you slice by cross sections. At the tiniest part of it, that would correspond
To the bottom.
with the bottom, and then as it gets bigger, as the cross sections get bigger, you would then fill in with those circles, with the biggest one in the middle.
No,
That's just something.
Oh yeah, wait, no.
It's just putting half and half on each side.
Yeah.
Oh,
Yeah.
I like separating.
yeah.
And then boom. So
Now I need to do this with paper mache
or computer software.
or computer software.
Let's take clay.
And clay.
Let's make an integrated project.
Play-Doh. That, you
Yes.
see now we're thinking like
Last year-
second semester seniors here. like computer software, write programs. No. Play-Doh.
What?
Get our stuff moving in the right direction here.
We used Play-Doh in math last year.
Yeah, we used Play-Doh last year.
Oh, like, they were making
We played with Play-Doh last
For
year.
in math?
Yeah.
And
When we were doing
Matrices.
oh gosh,
No, cross sections.
what's it called? Like ellipses. I forget the name of them.
oh, conic sections.
Yeah.
Yeah.
And then we conic sections.
Oh, these
Yeah, like
babies.
that.
Ah.
Yeah.
Yeah.
It didn't work.
That's not Play-Doh.
Yeah,
That's probably
So you're waiting with bated breath. So we have a relationship involving the radius and the height. The water is being pumped into the tank, so we have a rate of change involving the volume. So I can make note of that. That's going to be my dV/dt. That's the rate of change of volume in terms of time. All right. Again, if you don't reason it out from just the idea that a quantity of water is being pumped in and that would correspond to volume, just look at the units. Meters cubed, that's a measure of volume per unit of time. So rate of change of volume to time. Find the rate at which the water level is rising, so I need a dH/dt. When the water is 3 meters deep. Now, since the height is changing as water is being pumped in, I don't want to substitute that 3 in right away, because if I do, that's going to treat the h as a constant. Constant multiple or a standalone constant doesn't make a difference. It's going to treat it as something that's not variable, and it's going to impact everything. All right? If it varies, it needs to stay as a variable until you take the derivative. That's when you can do your substitution. All right? But the issue here is they didn't give me a dr/dt. That's a problem. Right? They didn't give me a dr/dt, and they're not asking me for dr/dt. But if I take the derivative of this, treating r as a variable, I'm going to get a dr/dt. But I'll have nothing to substitute in for it, and no way to make that determination, at least seemingly no way to make that determination. All right? And I can't just substitute a value in for r, because r is going to change. If I fill this cone with water, depending on its height, the radius of the surface of the water is going to be different. If the height is up here, it's going to have a much larger radius than it does if it's down here. All right? I got to get these things out of here. Tape down, I'll do it later. Anyway, so we need a way to get rid of the r. And this is where your level of understanding is solely dependent on my ability to draw this correctly. So you have to root for me on this one. It's not going to be pretty, but okay. Yeah, it's not bad. It's not bad. I'm off to a good start. All right. So, at any height along this journey, I guess, as water is being pumped in, blue. All right, so those radii, there would be radii corresponding with each moment in time that the water is increasing in height or decreasing if it's draining. All right, but there's a radius that's never changing related to the overall size of the structure. All right. Also, you have a height of the water corresponding with the moment in time related to that rate of change associated with the water being pumped in. All right. And you have an overall height of the water basin itself. All right, so now this is where you sort of have to suspend your disbelief a little bit, and maybe I do need some Play-Doh, because what I need you to kind of imagine is a clay or piece of Play-Doh shaped in the form of a cone, and I just cut out a quarter of it as a wedge. You gotta imagine what the cross sections that would remain would look like, all right? At this point, at least until I get the Play-Doh in here, I'll probably find an applet online. Those cross sections, or at least one face of the cross section, is going to form two overlapping right triangles. And those two overlapping right triangles will be in proportion, right? So if I were to cut out a wedge of this, it's a conical shaped wedge of cheese that I'm cutting out, and it's delicious. And what I have here, this piece, is that face that shows when you look on the cone, all right? So I have a radius here that's known to be 2, and a height that's known to be 4. Those are known quantities, they don't change. I have a radius that's unknown here because it's dependent on the moment in time in which you're interested, right? So you have some piece of information that tells you, all right, stop the clock here. That's the R that I care about. But unless I have that information, I don't know what the R is, so we just call it R. And that would correspond to some unknown height, some varying height, all right? From this, I could then say that R to H corresponds to 2 to 4. Or I could say that R is equal to 1/2 H by cross multiplying. All right, so I have a relationship between R and H, a variable relationship, all right? Which is good news because that's going to allow me to swap out the R here. I could have gone about this one of two ways. I could have taken the derivative with the product rule, not too crazy because it's polynomial based anyway. I could have taken the derivative, got a dr dt in there, said, oh dang, what do I do? Then do all this work, take the derivative of this, and then substitute in. That wouldn't be the end of the world. But if I do the substitution now, it's going to make my calculation a lot easier. I'd rather that be the case. So that's what I'm going to do. I'm going to replace my R with a 1/2 H. So V will be 1/3 pi times 1/2 H squared. All right, if I square the 1/2, I get a quarter. Multiplied by 1/3, I get 1/12. Multiplied by pi makes a pi over 12 coefficient. H cubed, H squared multiplied by the H. All right, much nicer to take the derivative of this because it's a function of one variable. And I only wanted to relate volume and height in effect anyway. The radius was fine, we needed to find a relationship between the height and the radius. So dv dt would be equal to pi over 4 H squared dh dt. All right, we're looking for dh dt. They gave us dv dt. Water is being pumped in, so it's a positive 2. If it were being drained from it, the height would be decreasing, the volume would be decreasing, so those would be negative quantities. They're telling us the water will be 3 meters deep. Just be careful. I won't do this to you because I'm not too terrible when it comes to stuff like that, but the AP, you never know. 2 cubic meters per minute and then 3 centimeters. You know, just be careful about shifty unit changes, you know. And then, of course, a multiple choice question that has the choice related to you not making that identification. All right, so what do we have here? 9 pi over 4, so 8 pi over 9. H dt 8 over 9 pi. And then units, again, I just talked about them, but I forgot. Meters is a linear measure per minute.